Hey there everyone, welcome back to another video. Today we'll be looking at properties of waves, IGCSE physics. Let's get started. The first thing we'll be looking at is describing waves. A wave is any disturbance moving from one point to another, carrying energy through a medium or without the medium as a whole. Now we'll be looking at the parts of a wave. The top part is called the crest, peak. This part is called the trough. The amplitude is the maximum displacement from the baseline or from the surface of the ripple tank, as we'll be looking at. The amplitude. Wavelength is the distance from one trough to another trough or from one crest to another crest. Okay, yeah, never mind. Wavelengths and amplitude. Waves are often represented as a wavy line. This wavy line is like a downward slice through the ripples in the ripple tank. It shows succession of crests, also known as peaks, as we mentioned earlier, and troughs of which the ripples are made. The wavelength of the wave is the distance from crest one crest of the wave to the next. Since the wavelength is a distance, it is measured in meters. So unit of wavelength. Its symbol is lambda. It's a Greek letter. The units is meters. And then we have the amplitude, or A is the maximum distance that the surface of the water is displaced from its undisturbed level. That is the height of a crest or the depth or of a trough. Its symbol is A. So the symbol of amplitude is A. And let me just clear this. This distance is the amplitude, and this distance is also the amplitude. Next, we'll look at frequency and period. The frequency, or f, of a wave is the number of waves sent out each second. Frequency is measured in hertz. So frequency, it's hertz, hertz or Hz. 1 hertz is one complete wave or ripple per second. Then we have the period. Period is t. It is the time taken for one complete wave to pass a point. The period is measured in seconds. Period measured in seconds. Now this is the formula that we have. Wave, or let's say period, t is equal to 1 over f, or f is equal to 1 over t. Anyway, change of base, as you might know, change of subject, sorry. Then we have the wave speed. The wave speed is the rate at which the crest of a wave travels. Waves have different speeds. Sound waves travel at 330 meters per second through air, and light travels at about 3.0 times 10 power 8 meters per second through air, which is for light. Whereas sound wave travel at only 330 meters per second. So you can obviously see the difference, right? Then we have waves and energy. Okay, let's think of the speed of a wave as the speed at which it transfers energy from place to place. When a wave travels from one place to another, it is not the matter that is moving. The wave is moving and it is carrying energy. It may move through matter or even through a vacuum, but the matter itself is not transferred from place to place. A wave transfers energy without transferring matter, and this is something you should probably note down and always try and remember. Now, the bigger the amplitude, the more energy the wave travels. Let's look at an example. This is one, and this is another one. As you can see, obviously there's more energy being transferred than this one, right? Then we have waves, and waves are of two types, transverse and longitudinal. Transverse waves are waves in which the particles carrying the wave move from side to side at right angles or perpendicular perpendicular to the direction of the wave. You can decide not to add the propagation if it confuses you. Longitudinal waves are when the particles carrying the wave move back and forth. Back and forth means they move parallel to the direction of the wave. Examples of transverse waves are ripples on water, light and other electromagnetic waves, secondary waves such as secondary seismic waves, S waves. Examples of longitudinal waves are sound waves and primary seismic waves, which are P waves. So now longitudinal basically are just two of them, this and this. P waves and S waves are basically when we have earthquake, the waves on the top are the P waves and the waves below are the S waves. Now, yes, this is how the direction of the propagation moves for transverse waves, and this is how the propagation for longitudinal waves work, parallel to each other, perpendicular to the direction of the wave. Then we have speed, frequency, and wavelength. The speed V, frequency F, and wavelength lambda. So when we want to calculate the speed, it's basically frequency times lambda. When we want to calculate frequency, it's speed over lambda. And when we want to calculate lambda, it's basically speed over frequency. This is change of subject, change of subject. So you can decide to only memorize this and then basically figure this and this out. Then we have changing material, changing speed. When light travels from one material into another, they usually change speed. When it travels from one material to another, light travels more slowly in glass than in air. Sound travels faster in steel than in air. When this happens, the frequency of waves remain unchanged. This is really important to remember. Jot that down no matter what. Frequency of the waves is unchanged or undisturbed. This means that wavelengths must change or slow down. So yes, this basically. So we have the wavelength in the air. It's moving, okay. Then it enters the glass. What happens is the wavelength decreases, but the frequency remains the same. Then this enters the air again, and the wavelength becomes back to the original wavelength, and this continues. So inside the glass, it slows down and the wavelength decreases. Now, obviously, lambda 1 or wavelength 1 will always be bigger than wavelength 2, which is here. Then we have refraction in ripples. Know that this is not sound, sorry. This is in water tank, and we'll be looking at refraction of light in a different video. So we have our this thing going like this, and always remember this is going to be perpendicular to the direction of the wave. This is the direction of the wave. Now this is the deep and fast side, and inside is the shallow and slow side. What is going to happen is that this is how you draw the normal. It should be 90 degrees with this slope, I guess. This causes the direction of the wave to change, and this eventually refracts this thing, bends towards normal, and the normal is an imaginary line. That's why it's dotted. Yes. Then we have reflection in ripples. So we have, again, this should be perpendicular to the direction of the waves. Going like this, we have our imaginary line normal. So what's happening this time is that the angle of incidence is angle of reflection. What this means is that from the imaginary line, the normal, the angle formed over here is the imaginary angle. And when it's reflected, the angle formed here is the reflected ray or the reflected angle. The barrier acts as a mirror. This barrier, it's acting as a shiny surface when it's in terms of light, shiny surface, but a mirror over here. That is why this is proper reflection because the angles will be the same. Then we have diffraction. This is the spreading or bending of a wave as the wave passes through a tiny gap or meets an obstacle. Waves are diffracted when they pass through a gap or around the edge of an obstacle. The size of the gap affects diffraction. The effect is greatest when the width of the gap, let's say this, is equal to the wavelength of the ripple. So this distance r, let's say, is equal to distance r. That's when the effect is greatest. When the gap is smaller, the wavelength or do not pass through at all. So if this is how it is, this is r. Oh, sorry. We have 1, 2, 3, and this wavelength is q. If r is smaller than q, then the wave will not pass. This is basically it. Let me change the color. Normal diffraction, 1, 2, 3, diffraction around. Then we have normal diffraction again. The width or the distance over here shows us how much it's going to diffract. Over here, this lambda or r, lambda is greater than r, so it cannot pass. Then we have another case where it meets an obstacle. That's why it bends like this. And